Hello, Assalamualaikum warahmatullahi wabarakatuh. Okay, continue again our class today, or this time, our lectures is about new topic about ideal reheat Rankine cycle. I hope what I have told you last time or last previous class, that mean you have recovered or you have learned something new and you are ready for the examinations and also for any task that will be given to you or anything when you will become as a engineer. Okay, I will share for you one slide. Uh, okay, let's look on the slide about reheat Rankine cycle. So this is a reheat Rankine cycle. This is normally the schematic diagram of reheat Rankine cycle. If you see here, what difference between reheat Rankine cycle and only Rankine cycle? That means in the reheat we have two turbines because one of the turbine number ones the will be used to turn the shaft, and from the energy come from the boiler, and then after that the steam that come out from the first turbine or the first one is called as the high pressure turbine. So the energy will be less than the actual one, the actual one. So the first one. So the steam will be transferred again to the boiler, and at this state or at these situations, the steam will be reheated by the reheater. So then come out from the boiler with a new energy, and the energy, this steam with a new energy will turn to the turbine number 2, low pressure turbine, and then the energy will be used to rotate the rotation, to rotate the shaft and give a rotations and give a power to the generator. So this steam will come out from the turbine number 2, so it come to the condenser and go to the pump, and this process will be continued. Okay, let's look on the number 2, what it said: expand the steam in the turbine in 2 stages and reheat in the between, and this called is reheat. Okay, this is a TS diagram, temperature versus entropy diagram. Maybe number 1, number 2, number 3, and number 6. This is all the points, all the stages that you have known before this. The new one is number 4 and number 5. Okay, because we have 2 turbines, so they must be, this cycle must have 2 lines. That means line number 1, that means 3 and 4 is for high pressure turbine, and line number 5 and 6 is for the second turbine, is for low pressure turbine. So in the between this line, it have a reheater to doing the reheating process of the steam. So as you look in the TS diagram, the line is assumed as the isentropics, okay, because we assume turbine as an adiabatic, also isentropic. So the process must be follow the isentropic law. To analyze this, you only add for the Q in, because as you see in this picture, in this diagram, or in this TS diagram, they have 2 turbines. So in between 2 turbines, it have also the reheater. So in this system, there are 2 one reheater, but at one reheater have 2 process or 2 functions. Number one, to heat the steam at the boiler in the first stage, at state number 2 and number 3. And another reheating or reheat happen at process 4 and 5. So Q in, you have Q primary and Q reheat. So to calculate the amount of energy in the system, so you have to do or you have to take heat in the primary and also plus the heat in the reheater. So using this Q primary and reheat, so you simplify the equations, delta H for points or stage 3 and 2, and also for reheating or reheater, it at state 5 and 4. So this is analysis calculation for how you can get Q in. And then let's see for work net. So if the Q in have two functions in the reheat Rankine cycle, is also same as a work out or work net. So work net, you not have only one work net in 3 and 4. Okay, work out in 3 and 4. You have to take 2 work out. That means 3 and 4, and also 5 and 6, because this is where the energy is come out from the turbine. So from here, work out will become work turbine number 1. That means at high pressure turbine, plus work turbine number 2 at low pressure turbine. So put in the equations delta H, because we want to use H because this working fluid used as a water, so as a steam water. So you have to see your method of analysis or calculation is based on the properties table. So you put there is delta H, H3 minus H4 plus H5 minus H6. That means 5 and 4, 5 and 6, 3 and 4 is depends on the point or stage where it is come from. Okay, so from here you will get the total of work work out for this reheat Rankine cycle. Okay, the single reheat in the modern power plant improve actually the cycle efficiency by 4 and 5%. That's mean by increasing the average temperature at which heat is transferred to the steam. During the heating process, by increasing the number of expansion or reheat stages, that means by increasing the number of stages, expansion and reheat processes approach an isothermal process at the maximum temperature. So the use of more than 2 reheat stages is not practical, because when you use more turbines or also more stages of reheat, what happens, the temperature is will become almost isothermal. So that means the practical method, you want to improve this cycle by using reheat, only put 2 turbines. Okay, so the reheat temperature are very close or equal to the turbine inlet temperature. Okay. Let's see the sample problem. Okay, consider a steam power plant operating in the ideal reheat Rankine cycle. Steam enters the high pressure turbine at 15 megapascal and 600 Celsius. and is condensed in the condenser at a pressure of 10 kilopascal. If the moisture content of the steam at the exit of low pressure turbine is not exceed 10.4%, determine A, the pressure at which the steam should be reheated. So you have to find the value of pressure where it should be heated, either number 1, 2, 3, 4, and 5, 6. B, the thermal efficiency of the system. Okay, actually this sample problem is have give you the schematic diagram of the turbine reheat cycle system and also the TS diagram for the system. So maybe in the exam or in the actual situations you don't have this diagram, but you have to think and you have to analysis and then draw the new schematic diagram based on the what cases or what problem that you feel or you want to solve. Okay, it also correct. It is also followed by the TS diagram. Okay, this diagram actually for the reheat. Okay, reheat. Normally the reheat only have 2 turbines. It's more than 2. It's not practical, but if in the actual cases that have more than 2 turbines, 2 reheater, so you have to draw more line in here. Okay, let's go for the solutions. Okay, for the solution, please refer to example 10.4, page 566 book. Chengong. Okay, let's go look on these pages. Okay, Russian. Okay. This is a solution. Okay. 466. 466. 466. 467. Okay. First of all, you know the question is about a steam power plant operating in the reheat cycle. So you have to consider this a reheat Rankine cycle. So it have a moisture content in the turbine exit, and the assumptions that you have to do is number 1 is assume that it is steady operation condition exit, and then number 2, kinetic and potential energy changes are negligible. So from the analysis, it also have the schematic diagram of the power plant and also TS diagram. So from here, you know that for A, the reheat pressure is determined from the requirement that the entropy at state 5 and 6 be the same. Okay, state 5 and state 6. So at state number 6, we know that the pressure is 10 kilopascal because it has been given in the questions. And the moisture contents is 0.896 because it said or it mentioned in the question that the moisture content must not exceed 10.4. So 10.4%, so we take 100 minus 10.4%, and then we get the moisture content is 89.6%, so minus divided by percentage, so you get 0.86. So because in state number 6, it is mixture region, so to find entropy, remember when I said when the case in the mixture region, so you have to find the equation that have situations of fluid and also of liquid. Okay, two conditions in one equation. So using the equation SF minus S6 SFG, so put down all the values that have been given, and we have find here 0.6492. This is SF at 10 kilopascal. So this value you can find in the properties table at 10 kilopascal, and go to the specific properties and find SF fluid. So you will get 0.6492, and also SFG is FG minus SF. So this is the value, and then from there you calculate, you will get S6 is 7.3688 kilojoule per kilogram Kelvin. So also from there, based on 10 kilopascal, using the same equation method that have in the wet region situation, so enthalpy H will get the answer when you put all the value here is 2335.1 kilojoule per kg. Okay, so you also know the temperature at T5 given in the question 600, and the knowledge of thermodynamics, you know that if it at the same turbine, so the entropy is the same. That means entropy 5 is equals to entropy 6, because this is isentropic process. So using these two properties, and these properties actually is in the superheated region, so open your properties table to the superheated table. At there, find the temperature 600 and also the entropy of 7.3688. So from there you will get you will found that these values, two values in the column of pressure 4 megapascal. Okay, 4 megapascal. So at that point you also take H5 as output, because this enthalpy state number 5 will be used in next finding. So therefore, from here, steam should not reheated at a pressure of 4 megapascal or lower, because to prevent a moisture content above 10.4%. Okay, that is the answer. The answer P5 is 4.0 megapascal. Okay, we go for the B. Okay, how to determine the thermal efficiency. So to do this analysis and calculation thermal efficiency, we know that we know the thermal efficiency is based on the equation W net over Q in. So at each stage, starting from state number 1, using the data that have been given in questions, find H1. H1 actually based on the TS diagram, H1 is equal to HF at 10 kilopascal. So using the properties table, you can find the value of 191.81 kilopascal. Okay. State number 2, also P2 is given 50 megapascal. So you know that is isentropic process at that situation of at device, that means pump. So S2 is equal to S1. So using the pump formula, V delta P, so is equals to put all the value that you know in here, and then you will get the work pump in, okay, for that process. So from the work pump in, you also know the work pump in is equals to that delta H, that means H2 minus H1. So from there, H2 you can find, and then you will get 206.95 kilojoule per kg. This is H2. Okay, then go for step number 3 using P3 and T3 that has been given in the question. This is the two properties that you can use it to find in the properties table. This is superheated because you know 600 is more than saturated temperature at 50 megapascal. So straight away find H3 and S3. Okay, step number 4 we has also covered, also find in A through to know the efficiency percentage. So you also have to find Q in and Q out. Okay, Q in have two at two process. That means at process 3, 2, and also at process 5, 4. So put all the value here, and then you will get Q in. Q out is only at one process, that's been at the condenser HN1. So put the values that you get above, then you will get Q out. And then using the equations that this equation actually you don't remember. This is from the derivation. So the basic formula is thermal efficiency is W net over Q in. So when you derive that equation, it will give this equation 1 minus Q out over Q in. So using this equation, put all the values, then at the end you will get the final value of 45%. This is the thermal efficiency for reheat Rankine cycle. Okay, this is for me. This is quite simple. Simple problems that you can solve. Actually, you have to do it yourself, make it more easy, do again and again to know the process, to know the method, how it solve the problem. If you got any question or any that you cannot remember, or you don't know where it comes, so please give me a WhatsApp, or please ask me any question. Okay, I will answer whatever you want to know about reheat Rankine cycle. Okay, that's all for this time. See you in next video or in next lecture ODL. Okay. Assalamualaikum warahmatullahi wabarakatuh, and bye-bye.